Tangents. We're in 8-4 now today, talking about chords and arcs. So we've got two circles drawn here. What of our four segments here would be congruent? And yeah, so we said circle A is congruent to circle D. The equals of the squiggly is congruent. Angle A is congruent to angle D. BC is 15. Could we figure out EF? Mackenzie?
I was going to say, okay, so I think it would be 15 because since A is D, I thought you said A was the same as B.
A is congruent to B, or D, sorry.
Yeah, I thought you said B.
Jacob?
So the radiuses for these two circles are congruent?
So the radii, that's fine, you can say it either way. So AB right here and AC right there, those are congruent, we know that. But since the circles are congruent and the angle, well, A being congruent to D doesn't even matter, like the angles. Since the circles are congruent, I know these radii are congruent to my other radii. What can I use that for?
Well, can't you use like the hinge theorem?
Yeah, to what? Okay. To prove that they're equal?
You can use SAS to prove that these two triangles are congruent.
Okay, so we could use side angle side to look at them being congruent because we've got the sides are the radii and the angles we've been told are congruent. Curious if anybody else can kind of make the jump. Because we can draw anything we want on this circle, right? So couldn't I draw another radii that would be parallel to BC? Like let's, for a minute, and I think we're going to hit a problem like this in our lesson. But for a minute, think about if we only had one circle and we wanted to solve things about it. One thing that I really want you guys to start to get in the habit of is think, what can I add to this drawing? What can I put in to help myself? Because if I drew a radius congruent to BC, and then I drew another line down, let's just call this EF, we'll call that G since we haven't used G. What do I make now? What kind of shape? Parallelogram, right? So kind of just keep that idea in your head of when we add things to our circles, we can make other shapes happen. So we do know that due to the radii being congruent, due to everything being congruent, that EF and BC would be congruent.
We have to learn 6 theorems today.
We have to find the link though.
Yeah, like.
Yeah, so it'd be 15.
Wait a minute, that's not 6.
Yes.
That's
7, Smart.
We know they're congruent.
That's 79 to 85. But like, don't we have to know that angle A is
Congruent to angle D?
Yeah.
We do.
I thought that just says triangle. Oh, okay. I didn't read it all. Okay.
Yeah, that's important information.
'Cause I didn't see that, so I was really confused.
Like that would be one.
So, first theorem here is talking about within a circle. I gotta remember which ones are which. I'm actually probably just gonna look on the notes. Within a circle or in its congruent circles, congruent central angles have congruent arcs. So, if we know that angle O, the blue angle O, and the red angle O are congruent, then their arc lengths are going to be congruent. We know that because, I mean, arc lengths are directly related to the angle size. Also because that, so if we're talking about chords and arcs today, what's the difference between an arc and a chord?
What is it?
You know, it's 3 notes you play together, it sounds nice.
Well, yes, but
I figured you'd like that
Actually,
answer.
it could be 2. Is it?
That poster has fallen down, so you can't even use
actually
that,
there
Jake.
can be 4 notes in a chord.
So
I-
arc is the part of the circle's circumference?
So an arc is part of the circumference.
Ooh, is a chord
While
like a
the
line?
chord is- while the chord is it's the like connection between the 2 points that are surrounded.
Yeah, so if I have an arc right here, the red line is my arc, the blue line is my chord.
I knew
So the
it.
chord is the straight distance between the 2 points on the circle. The arc is the distance of the circumference, the piece of the circumference that is the distance between those 2 points. Yeah.
So like the chord is like the displacement.
Yeah, the chord is like the straight way to get from one place to the other.
That would be displacement.
So then now we have the same.
That's first quarter sense.
We have the same theorem essentially, except for now it's talking about the chords as opposed to the arcs being congruent. Theorem 81 is, so if I know that AB is congruent to CD, then the arcs that they have between them, so this blue arc from B to A and the red arc from C to D, those arcs would be congruent to each other. And the converse, if I know the arcs are congruent, then I know their chords are congruent. If we know that we have OE congruent to OF, so they're both portions of the radius, and since they're congruent to each other, then AB is going to be congruent to CD. Because think about it, the distance away from the center of the circle will determine how long that chord is. And then likewise, if AB is congruent to CD, then the distance from the radius, or from the center point out to them, is going to be congruent. Our diameter is perpendicular to a chord. Then the chord itself, what about it? This is really cool, so I want you guys to take a second to look at it. So then CE is congruent to ED, so that diameter bisects my chord, and the arcs are equally bisected. So CA and AD are the same arc. So if your diameter and a chord are perpendicular, and of course your diameter you can spin around wherever you want it to be, so the diameter will bisect your chord and your arcs. So wherever, like, once your diameter bisects the chord, or once it's perpendicular, then you know it bisects. And
I understand it now.
yeah, and so likewise, this is kind of like the converse. If the diameter bisects the chord, then it is perpendicular. So I don't know why that wasn't lumped with Theorem 83. And to finish this out, Theorem 85, if AB is a perpendicular bisector of the chord, then it is, then the center must be O.
Are we gonna do 2 chapters?
No. This is just a lot of theorems that we, and really as we use them, they make more sense, and it's not like you have to memorize it, you just have to remember how to use it.
This feels like it's just gonna be a really short chapter. Thank you, Greg.
So, we know that BC is congruent to DF, so we have congruent chords. What else, what all can we conclude? Grant?
The arc, DF, and BC are also congruent.
So, and how do we, so our notation up here was for the chords, right?
Yeah.
How do we notate for the arc?
Put an arc over
Put an arc over it.
Really?
So DE is congruent to, or DF, sorry, is congruent to BC.
And then BOC and APF are both right angles, so that makes sense.
So, wait, how do you know they're right angles?
Because I like them to be right angles.
Well, that's not a good enough reason. I will
Oh, wait.
agree with you that we
They're
know
congruent. Sorry, I don't know why.
angle O is congruent to angle P, but we don't know
I
what
don't
their
know why I
measure
said
is
right
right
angle.
now. I mean, they look like they could be right angles, but we don't know it, so we can't assume it. What else do we know? There's more information. It's kind of like duh, but since we want to write down all the information we can, Grant.
BO is equal to BP. PF is equal to OC. Thank you, Seth. The triangle DPF and the triangle BOC are congruent by side.
Yeah, and then the triangles are congruent based off side, angle, side, or any number of theorems that we could use. Side, side, side will work too, since we've already proven that the chords are congruent. So the last thing will probably be BOC
Bach.
is congruent to order matters. So DPF.
DPF.
Yeah.
Did you hear about that?
Okay, that's
Yes,
all
I
the
did,
ones
but
that
let's
we
not
have.
talk about it now.
I thought there was one.
Alright, so try this on your own. All we know here is the circles are congruent, and you know an angle congruence. Based off that, work it out. You know, maybe, we might start the next lesson today, but only maybe.
How do you show that as a chord? Or do you just
The
draw a
line
line?
above it, because it's either a chord or an arc. Like it has to, those 2 points are on the circle. Now you're on the guy at the part one.
Wow, that was
So your circle's congruent, and your notice that that angle is not the central angle. It's the angle made by a radii and a chord. So one notation that I'm seeing a lot of us do is just notate that the radii must all be congruent.
Oh, see.
Anyone think they can talk me through this? Mackenzie?
Well, since you know, like even though it's not the angle in between the exercise, you can't say yet that it's like that they're congruent. But since we have angle B, like OBC and PDF, I think you could say that the other side is also like BC, same as.
So based off, here's the problem. Right now we have angle side side.
Yeah, that's what I was saying.
So what could we do first then? We can't really show triangle congruence based off angle side side. Seth, actually we haven't talked yet today.
Since 2 of the sides are congruent, it's an isosceles triangle, which means that angle C, angle OCB is congruent to angle OBC.
Wait, so OCB, so now this angle is going to be congruent to angle B, right? Because the isosceles triangle, and because of that, the same holds over here for angle F. Then based off that,
Then you can do, I think, either angle similarity, or you could do angle side.
yeah, we can do angle or angle side. We also know that that means that angle P must be congruent to angle O. Now we really just prove what we want to, because we can either prove the triangle is congruent first, or because my 2 congruent angles, the third angle left over has to be congruent because of CPCTC. The congruent parts of congruent triangles must be congruent. So it's all just about what can we set up first. And you can't stop when you do have angle side side. You have to show the other 2 angles, or you have to show like the other angle pair, so you at least have 2 angles to work with. Is this easy enough? And just for posterity, let's see what they, we'll capture that up there.
Wait, what word did you say?
Posterity?
No, we just wait. Is that the one we just?
No, it was like
Perpetuity?
No, it
Propensity.
was proprietary.
Proprietary.
Yeah,
Oh.
That's it.
It was something.
Propensity.
Yeah, that was not it.
You guys are just saying like all the
There,
big P words that you can.
Whoa, bro!
Wait, I think
This is
I-
school property.
In this problem, you will find the length of a
Oh, propensity.
Yeah.
Propensity? What does propensity mean?
It's like what you normally do.
How you
Yeah, like he has a propensity to come to school early.
Like Ethan has a propensity to eat hot pockets. Oh, it's not the
Why does everybody love hot pockets?
bad for you, actually.
Me
All right,
too.
so now we need to find the length of an unknown chord. So now we only have one circle to work with. We know that because OP is perpendicular to PR, it's going to bisect it. So PQ is now congruent to QR. I know PQ is 12.5, so I would also know that QR is 12.5. So right here would also be 12.5. We need to figure out the length of RS.
Okay.
Straveler?
Well, by theorem 82 is converse. It says that if like OQ, we could label that.
So you're saying OQ.
Is congruent to. Can we like make a point there?
Oh, yeah, let's determine T.
Yeah, it's congruent to OT. Yeah, then by theorem 82 is converse. It says that then PR has to be congruent to RS. So if you just multiply 12 by 2, then you get RS equals 25.
Yeah, so RS here must be equal to 25. Because based on, was it 83? 82 in its converse. Because the distance from the center to the chord is congruent, then the chord lengths must be congruent. Just think about it. As we get further from the center, my chords will get shorter. As we're closer to the center, my chords are longer. If we're the same distance, the chords are the same. And it stands to say, just to have that detail there, we have to see that both of these have right angles. Now we saw it, it's part of the theorem, but if you don't have the right angles, you can't necessarily apply that theorem. You'd have to check if the angles were right first. Seth?
On our paper, it didn't actually have the right angle.
No, I took the picture too soon then. It
How
must have
dare
taken,
you?
like when I do the screen capture. Yeah, but it's there. My bad. Yeah, thank you for pointing that out. Right on, he's talking about on the problem 2, right, the bottom right angle at Q wasn't there in yours. So if you want to go ahead and draw that in, that might be a good reminder on your homework. So, Sasha, I just saw you quickly jot this down. What's X going to be?
16.
Why?
Because the one there bisects it, so it'd be, since it's a right angle, it's
Yeah.
perpendicular. So it'd be also 18 and 18, which means X is 16.
Yeah, we see the right angles. We see that since this chord is 18 and 18, it's really 36 combined. So since this chord has the same length, the distance from the center out to it is going to be the same distance. So that should be kind of a quicker one. On part 3, now we only have, so we're talking about pieces of like a clay pot. Archaeologists a lot of times will have to reassemble things. They'll find lots of pieces. So and I did this for you. I wasn't going to make you guys trace this out on your paper. So it would just take some time. So to do this though, to make sure that the distances are equal, we can use a compass. We can lock the compass and make the arcs on the outside of our circle and the inside. And then we connect those two intersections of the arcs. And then if I do it again, it'll find my radius or my center point where those two lines touch. So our goal here was to figure out what is the radius. We have chords perpendicularly bisected by pieces of my radius. And then we could just measure. So if you physically had the object and you could trace a part of it. So they're talking about like you have part of a clay pot, it's round, you only have a portion of it, you figure out, you just set two congruent chords. From those chords, you do the little tracing on the outside, inside, connect all your points, you find the center, you can measure the radius. So of course, not having you guys do it, but I will have you guys do this. Not the coin. Sorry. Thinking ahead.
Dude, throw me a coin. I'll trace it.
So we need to find the measure of r.
In
So what we have set up is we have a right triangle here. R is my hypotenuse and it's a radius for the circle. I'm told what LM is. What can we do? That's good that everybody's hands shot up, Greg.
So you can use the Pythagorean.
How so?
Well, LM is 14 centimeters, and since you see the right angle,
Since it's perpendicular, what do we know?
we know that LN is congruent to NM.
Yeah, we know it bisects. So LN congruent to NM. Very good.
So LN is 7,
Okay.
and then you find 7 squared.
Yeah, so once we find that LN is 7, then it's just using the Pythagorean. So, sorry, went too far.
How dare you?
How dare I? So then we have both legs, we use our Pythagorean theorem. Try the got it. I think this is this is the one that I gave you guys.
The one where you have to explain.
So we're going to do two things here. We're going to find y. So that's the first thing that you want to do.
What's 15
And
squared?
then we're going to answer the got it question.
Wait, is angle C like 90 degrees? Like,
You tell me. Actually, you can tell
because it's
based
11.
off the drawing. So Greg asked a really good question here that for a second had me a little confused. Like why the angle wasn't there. So he said, is angle C 90? Who can answer that question? Robert?
Because since it, you can see that AC is congruent to CF, then you know it bisects, you can tell right there, right angle, bang.
Because I see that line off my radius, or that line off my center, has bisected a chord, then because it has bisected, it must be a right angle.
So what is it?
So from there, we also know that if I draw that dotted line like you have on your paper, what about that dotted line? Sasha?
It is also a radii.
It's a radii, so what's it going to measure? 15. So then, we can do 15 squared, 225, minus 11 squared, which is 121. We get an answer of about 10.2.
Dude, I actually just got.
I know. Because I ran out of space on the paper, so I put the picture from this section, but then the got it asks us a different question. So for our got it, it asks, how does the auxiliary BA make this problem simpler to solve? Well, we drew it in because we know why it makes it simpler to solve. Kenzie?
Because then you have a triangle and you just use the Pythagorean.
Yeah, and we were given the radius, but not in the location where we wanted. So again, that whole thought process of what can I draw in, what can I add to my drawing to make life easier. Well, we know the radius, just spin it around to the location that you actually need it in. Man.
I thought we would have to do another lesson.
Yeah, what is, let me look at what the
Just
next
give us
one
our
is.
just work on our homework.
Yeah, of course that's what you want to do.
Of course. What else? Well, besides throwing a party, but
Or go to lunch.
Yeah,
bit
lunch
early.
would not
Let's
be
just
ready
go to
for
lunch
you
right
guys.
now.
What about the gym?
It
Nico?
sounds like it's okay.
What about Nico? Who goes to the gym? What's Nico?
Inscribed angles is pretty quick as well. So know that if we make up time now, like if we get ahead, I will give you back that time later, so like in the form of a work day or something like that.
Are we doing more notes?
Yeah.
Oh, then
We're gonna start at least.
I was gonna ask Wyatt if you want to work on it.
It's a back.
mean when an angle is inscribed? Greg?
In the circle.
It is in the circle. Okay, so what do you mean by that?
Like goes from point to point on the outside of
I have an idea. There we go.
like on
So it's an angle formed within the circle using points on the circle, right?
Yes.
Oh no, more theorems.
I did not want to customize.
Whoa, hold up. Yes.
I'm going to skip the solve it just so we can dive right into it. So check out our theorems here. So our first theorem here, 86. If an inscribed angle is from the circumference, from a point on the circle, not just in the circle, but on the circle, to two other points on the circle, that angle is going to measure half the measure of the arc. So angle B, the degrees of it, will be half the arc measure from A to C. So now what if, well, I mean, they're all in your paper actually, so I don't know why. What if? So if A goes from, and I probably need to highlight. Angle A uses those 2 points. Angle B uses these 2 points. So what do we know about A and B? They're going to be congruent because they're using the same arc. So both of them, A and B, are going to be half of that arc measure, whatever points we would call it, like C and D. An angle that inscribes to the a semicircle, so essentially the points of your diameter, has to be a right angle. So no matter where we would move that around the arc, it'll be a right angle. Your leg lengths will change, but it'll be a right angle.
So theorem 86, it works with any angle, even if like AB is not congruent to BC.
So this theorem 86 or what?
The other.
Or the one before?
Yeah, the one.
The one with the right triangles or the first part of it?
The first theorem.
This?
Yeah.
What was your question again?
The inscribed angle theorem.
Yeah, what's your question again?
No, not the corollary. So would it still work even if BA was not congruent to BC?
How do you don't even know that BA is congruent to BC. Yeah, that's not part of the theorem. That doesn't have to happen. Because if we look here, I definitely know that, let's say that this is C and D. I know that BD is not congruent to BC. Nowhere close. But still, the angle measure will be half of whatever this arc length is. AD and AC, those look like they could maybe be congruent, but it doesn't matter. That angle measure will still be half the length of the arc. Make sense? So, opposite angles of a quadrilateral inscribed in a circle are supplementary. Now, why? Take a second to think about why. Angle D uses the points AC. So, D will be half the length of this arc. Angle B uses the same points, AC, but now it's going to be half the length of this arc. What is the total arc length? If we talk about radians, don't care about the size of the circle. If we just go straight from degrees, well, not necessarily radians, but what would be the arc length of an entire circle? Mackenzie? That's half the arc length of the entire circle. Yeah, so this, let's say this arc length here was, like the blue one is 210. Then this arc length here would have to be 150. So half of that, they're going to combine to be 180. That's why they're supplementary, because between the two of them, they use the entire arc of the circle. That's why the opposite angles would be supplementary.
Wait, do you mean 360? You actually mean 180?
You said 180.
360 would be the whole arc, but the angles then, because they're half the arc, will be 180 when combined.
Oh, okay.
Yeah?
Yeah, just making sure.
Why are the angles half
So we can work through the trig and show that. It's just like what the gap that they open up, the perfect circle distance between them, that length is going to be double the angle measure of that interior angle. But again, it's not, you have to kind of think in relative lengths. We're not talking inches or centimeters, we're just talking arc length. Like there doesn't need to be a label. The measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. So read that again for yourself. Either angle C there, whether we look at the left circle or the right circle, will be half the measure of the arc BDC. So whether it's the small arc or the big arc, it all depends on what direction that tangent line is going. So the measure of an angle formed by a tangent and a chord. Now what if your chord passes through the center? If your chord passed through the center and you had a tangent line,
It's a 90 degree.
it'd be a 90 because this arc length would actually be an arc length of 180 because it's half your circle. So it takes up 180 of the arc. So that's why tangent lines to radii are 90 degrees. It's kind of like we learned that the tangent lines meet at a 90-degree angle, but this is why. Because when we work through the triangles and the trig that exists here, we get all those measures. So now, we'll just pass out the homework and work on that. I just wanted to introduce all those theorems so tomorrow it's a little bit easier for us to deal with.
My neck hurts.
You don't
I think I can put it back for a while.
You wanna put it back there?
No.
Okay, ow. Okay, I'm good. It's my
Pass them
back.
back to Robert.
Oh, I gave you
I
one.
need a nuzzle.
I already stole my pencil.
Ooh, hit her harder.
It's not nice.